Okay, so far in chapter 4, we've studied several historical solutions to the American problem of apportionment and how to apportion seats to the House of Representatives. Okay, we looked at Hamilton's method, Jefferson's method, Adams' method, and Webster's method. 4 of our founding fathers, methods that they, as non-mathematicians, just general scholars, invented as ways to apportion the House of Representatives. In 1929, Congress became a little fed up with the controversies surrounding apportionment. Every time there was an apportionment, someone complained that it was unconstitutional and would point out either a paradox or a quota violation. And they decided to ask a panel of mathematicians to recommend the correct formula. How do we do this? So the method suggested by the mathematicians goes by the name Huntington Hill after its 2 inventors. Congress actually didn't accept the recommendation until 1941, but when it did, it passed an act that made the Huntington Hill method the permanent apportionment method. It made the method self-executing, which means that congressional approval wasn't necessary each time seats were reapportioned. So what happens is every 10 years we take a census, and based on that census data, we reapportion the seats, and that happens automatically. So there is no fight in Congress about whether or not to reapportion. We said it has to happen automatically. And it permanently fixed the number of representatives in the House at 435. The only exception to that being if we add a new state, then we would add more seats to Congress. So the Huntington Hill method has stood the test of time so far. It's constantly being challenged by states that lose a seat under the method. Every 10 years, reapportion, someone loses a seat, they challenge, state challenges. And federal courts, including the Supreme Court, have all upheld it so far, but there are constantly lawsuits happening challenging the method and asserting that some other method is the correct method. So we're going to learn today about the Huntington Hill method. But in order to carry out the method, we have to take a small mathematical little detour, a little calculation that you've probably never seen before. Okay, so the standard way of averaging 2 numbers is to take the number halfway between them. And the way you find that number is you add your 2 numbers up and divide by 2, right? Standard average. That average is called the arithmetic mean, but there are other means as well. There's a geometric mean, a harmonic mean, and a quadratic mean, plus several other kinds of means. So the arithmetic mean is just one way of taking a number between 2 numbers. The Huntington Hill method uses this thing called the geometric mean. So this is what the geometric mean is. If you want to take the geometric mean of 2 numbers, a and b, it's the square root of a times b. So you multiply them together and then square root it. So it's analogous to the arithmetic mean, except instead of addition, we use multiplication. Instead of dividing to undo it, right, we add 2 numbers and then divide. Now we multiply 2 numbers and then square root. And for comparison, the arithmetic mean is a plus b divided by 2. Okay, so why do we even have this other kind of mean? So here's an example where we might use a geometric mean as opposed to an arithmetic mean. Over the last 2 years, the student body at Tasmania State University grew at a rate of 5% the first year and then 75% the second year. What was the average annual growth rate over the 2-year period? Not 40, why not? Yeah, so growing 40%, so if we said 40%, then that would be akin to saying that a 40% average growth rate means that growing by 5% and then 75% is the same as growing by 40% and then 40%. So let's see what happens. Let's just say we start with 100 students. just to make the calculations easy. 100 students. How do you increase 100 by 5%? Plus 5 students, yeah. So you would multiply by, okay, we don't actually have to do that. So you start with 100 students, we increase it by 5%. Then we increase that by 75%. How do you increase 105 by 75%? Yes, you got it. You multiply by 1.75. So I have 105 students, and then I want to keep 100% of them, so that's why I have the 1 in front. And then I want to add an additional 75%, so I multiply by 1.75. So I get 183.75. Well, you can't. So 100 is going to become 105, is going to become 183.75. Okay. So this is increased by 5%. This is 5% growth. And then this is 75% growth. So let's see, is that equivalent to 40% growth and then 40% growth? Because 5% and 75%, if you average them, you get 40 and 40, right? So if we start at 100 and grow by 40%, what would I end up at? 140. And then I have to take that 140 and grow that by 40%. Yep, so you multiply 140 times 1.4. And it's 1.4 because we want to keep 100% of it and increase it by 40%. So 140 times 1.4, and we get 196. So are these two equivalent? 5% and then 75%, is that the same as 40 and 40? No. So we can't just average them the arithmetic way by adding them up and dividing by 2. If I do the geometric mean, where you multiply them and then square root, let's try that. Okay, so 5% times 75%, and then square root in decimal form.
No, in the A and B.
Yes, 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 yes. So my geometric mean would be the square root of 0.05 times 0.75. And that's going to come out to 0.1936, or 19.36%. So let's see if that's equivalent. Increasing the number of students by 19% and then 19, if that's the same as 5% and then 75%. So I have 100 students. I want 19.36% growth. So how many students do I have now? 119.36. I know that doesn't really make sense, but you can't have part of a student, but this is just numbers. If we started with 10,000 students, we wouldn't have decimals. Okay, so now I want to increase 119.36 by 19.36% again. So how do I do that? Yeah, 119.36 times 1.1936. Take the amount you have now, 119.36. I want to increase it by 19.36%. So I have to multiply by 1 for 100% plus another 19.36%. And you get 142.47. Yes, sure. That's okay. Let's just compare though. So 142.47 compared to No, it was 183.75. What happened?
But the 40% growth is still not.
Didn't work. Yeah, the 40 and 40 didn't work. That one didn't work. Why didn't this work? Okay. So I'm going to do 1.05 times 1.75, square root that, and I get 1.3555. Yeah, so 35.5% increases each year. So let's see what happens when I do that.
I got 1.8.
Oh, you did? Let's see here. Oh, then you got to square root it.
Oh, yeah.
Yeah. So we start with 100 students. We increase by 35.55%. That is, you multiply by 1.3555.
Where do you get rid of the 1 then?
No, in order, when I say increase by 35.55%, to do that, you multiply by 1.3555.
By what? Right.
100.
Oh.
100 students times 1.3555. So I get 135.55 students. Now I need to increase that amount by 35.5% again. So I multiply again times 1.3555. And I get 183.74. So now that's a pretty good match. 183.74 compared to 183.75. Really close. We probably just rounded something a little different.
I think the only thing that's confusing, but I did it on my calculator, like the 135.55, was why, see where you say increase by 35.55.
Uh-huh.
I did that, but why does the 1 come up?
Okay, so it doesn't. Okay, so yes. So when I say increase by 20%, this is just a random example, right? To increase a number by 20%, that is equivalent to multiplying by 1.2.
Oh, okay.
Because you want to, if you're going to increase it, you want to keep what you have, right? That's the 100.
Okay.
So by using the word increase, I'm implying keep what you have already.
Okay.
So that's why here I just wrote increase by 35.55%. If I wrote increase by 135.55%, the 100% would mean double it. To increase something by 100% is to double. So to increase by 20% is to multiply by 1.2. Okay, so now that we've got that figured out, you try one. We have a population that grew by 10% one year, 6% the next. Find the average annual growth rate over the 2-year period. Go through it together. So we have a population of a town that grows by 10% one year and 6% the next. So I want to find a percentage that I could do the same percent growth by that same percentage for 2 years in a row that's equivalent to growth by 10% and then growth by 6%. Okay, so let's just see what happens when I grow by 10% and then by 6%. So say I start with 100 people in my town. grow by 6%. So I would multiply by 1.06, right? That's how you grow by 6%.
Oh, we did it by 10 first.
Oh, you do 10 first. Sorry.
By 1.1.
Okay, so we grow by 10% first, and you get 110, right? Okay, then you have to take your 110 and grow that by 6%. To grow by 6%, you multiply by 1.06. So 110 times 1.06 is 116.6. Yeah, just to make sure that everything comes out exact. Wait. Just wait. I'll answer later. So the question that is being asked here is, I want to find out what can I multiply by here times what times what. What can I multiply by so that I can multiply by that same number twice and get the same answer? 8%? How did you get 8%? Make right, but that doesn't Yes, I want the average annual growth over 2 years. So if I try 8%, let's try it. Let's do times 1.08, and I get 108, right? Times 1.08 again, and 108 times 1.08 is 116.64. So that comes out close, yep.
When you round, it comes out when you do it to the square root. It comes out like 1.079.
Yeah.
8 or something.
Yes, in the back. Yeah. Why? Why should I do that? Yes, so when they ask for the average annual growth rate, the whole point of the last example we did is that averaging your two percentages doesn't work. Okay, in this case, it came out pretty close, but instead of doing the arithmetic mean, the a plus b over 2, we're going to take the geometric mean, multiply them, and square root them. So my average growth rate should be the square root of 1.1 times 1.06. You take your two multipliers from earlier, you multiply them together and square root it. So 1.1 times 1.06 square rooted is 1.0798. Right, so 7.98% is my average annual growth rate. Yeah, which is really close to 8%. So in this case, the arithmetic mean and the geometric mean were really close. They're not always. Yes.
So where should you stop at the fourth decimal every time? How do you know where to stop?
Yeah. My general rule of thumb is like 2 decimal places. I should have made an example where it made a bigger difference. Let's do another example. Let's find the average annual growth rate for 10% and 85% growth. I don't care what you think. Here we go. So there's 2 ways to take an average, right? You can add them up and divide by 2, or you can multiply them together and square root. Which one is the way you average growth rates?
The square root.
Multiply and square root. So I'm just going to do it both ways so you can see why the square root is the right way. Okay. So regular average, we would do 10 plus 85 divided by 2. 95 over 2 is 47.5%, right? Okay. But then the geometric mean, I would do the square root of 1.1 times 1.85. Okay. So 1.1 times 1.85, 2.035, square root it, and I get 1.4265. As a percent increase, that's a 42.65% increase. So you can see those are pretty different numbers, right? If you could have a bank account that made 47.5% interest, you would choose that in a second over 42.65, right? That's going to make a big difference. So let's just see that the geometric mean is the same as 10% and then 85%. So if I start with 100 people and increase it by 10%, I get 110 people. Then I'm going to increase that by 85%, and I get 110 times 1.85, which is 203.5. So that should be equivalent to growth by 42.65% twice. So if I do 100, increase by 42.65, yeah, we were just doing this so that I could show you why we use the square root. So this comes out to 142.65. And then I'm going to increase 142.65 by 42.65 again. And I get 203.49. Very close, right? Yeah. So I can see that the geometric mean, increasing by the geometric mean twice, was equivalent to increasing by 10% once and 85% the second time. If I did this with 47.5%, let's just do one more where I show you that it's not right. Increase by 47.5%, the arithmetic mean, the regular old average, I get 147.5. Then I'm going to increase by 47.5% again. So 147.5 times 1.475, and I get 217.56. That's way off. All right. So the regular old average does not give you, is not equivalent to increasing by 10% and then 85%. So the answer is the geometric mean. And all of this other work is just to show that it's right? To show these two together, show that increasing by the geometric mean twice is equivalent to increasing by 10% once and 85% once. So this is just like a check.
So basically we should always use the GS.
For percent increases, yes. If you want to find an average percent increase. So in your text, questions 21 and 22, in this section are about the harmonic and quadratic means. So two other means, other than the regular average and the geometric mean, there are two other ones. And if you read those questions, they might make a nice little starting place for a project if you want to investigate those means and how you calculate them and what they're used for. Okay, so let's investigate the arithmetic and the geometric mean a little bit more. So for each number in the table, I want you to calculate the geometric mean and the regular old average, which we call the arithmetic mean. Go to it. So remember, Jefferson's rule was always round down. Adams' rule was always round up. Webster's rule was round conventionally. Below 0.5 round down and above 0.5 and above round up. So the Huntington Hill method uses a new rounding rule that you've never seen before. It's not round down, not round up, not round conventionally. It's a new rule. So this is how you round with Huntington Hill. If the quota is below the geometric mean of the lower and upper quotas, round down. If the quota is above the geometric mean of the lower and upper quotas, you round up. So you have to, so let's, for example, say a state's modified quota is 32.68. We have to decide how to round that. We have to take the geometric mean of 32 and 33, the lower quota and the upper quota. So take the geometric mean, 32 times 33, square root, and we get 32.496. Okay? Then is 32.68 less or greater than 32.496? It's greater than. So we round up. If you're above the geometric mean, round up. If you're below it, round down. So the summary of Huntington Hill is you have to find a divisor D, just like in Jefferson's, Adams, and Webster's method. We're going to use that same flow chart we've been using to help us find the D, right? And then we're going to use D as a divisor, compute each state's modified quota, and then you apportion the seats by using the Huntington Hill rounding rule. So we have a small country, 5 states, A, B, C, D, and E. We want to give out 40 seats using Huntington Hill. So we could start with the standard divisor. How do you find that? Total them all up, yep. So total all the population. So I 34,800 plus 104,8 plus 64,8 plus 148 plus 54,8. So there are 400,000 people in this country. There are 40 seats to apportion, so if I divide by 40, I get 10,000 people per seat. So I'm going to compute the standard quotas, where I'm using D is 10,000. 10,000 people per seat. So I'm going to divide each number by 10,000. So that is, I would move the decimal how many to the left to divide by 10,000? 4. Yeah. Dividing by 10 would be 1, 100 would be 2, 1,000 would be 3, so 10,000 is 4. So this is going to be 3.48, 10.4, 6.4, 14, and 5.4. So now I have to round these according to Huntington Hill. So in order to round them, I have to get the geometric mean between the lower quota and the upper quota for each of these. So for the 3.48, I have to multiply 3 times 4 and square root it, and I get 3.46.
Wait, why do you have to times it by 3.4?
The lower quota and the upper quota, right? 3.48, the lower quota is 3, the upper quota is 4, right?
Yeah.
So that you take the geometric mean of 3 and 4.
Okay.
That's 3 times 4 and square root it. Right.
3.46.
Right. Now, look at your number, 3.48. Is it above 3.46? 3.48. Bigger than
Above, yeah.
3.46? So you round up.
So now would 10.4 be 1.04? times
10.4? Okay, so for 10.4, take the geometric mean between 10 and 11. So you do 10 times 11 and square root, and you get 10.48. Is our number smaller than or bigger than 10.48? Oh, I'm sorry, I should have written these 8s down.
How do you find the number that you decide to round?
You take the geometric mean of the lower quota and the upper quota. So you round it down and you round it up.
So this one's equal, so
It's not equal.
10.488.
10 point, which one's bigger, 10.488 or 10.480? Right, my geometric mean is bigger, right?
So you round down.
So I round down. So the 6.48. To decide how to round it, take the geometric mean of 6 and 7, the lower quota and upper quota. So we do 6 times 7 and square root. 6.4807. Is my number bigger than or smaller than 6.4807? Smaller, so I round down. Okay, so for 14.08, I take the geometric mean of 14 and 15, square root. So I get 14.49. Is my number above or below 14.49? 14.08, bigger or smaller than 14.49? Smaller, so I round down. All right, so let's look at the 5.48. Take the geometric mean of 5 and 6. 5.477. Is my number bigger or smaller? My number is bigger, so I round up to 6. So let's see, if I add these all up, I need to come up with exactly 40. Otherwise, I have to think of a different divisor. 4 plus 10 plus 6 plus 14 plus 6. 40. Oh, good. I didn't want to do that again. So that's my final apportionment. Go ahead. If it didn't come out to 40, you would have to change your divisor. If it was too few, you'd make D smaller. Too big, make D bigger.
Oh my god. What's going on in that?
I don't know what's happening right now. Oh,
Oh.
here we go. Yeah. Okay, so just for comparison purposes, let's see what happens if we apportion the 40 seats using Webster's method. And I am just giving you a number that works, a divisor that works, so we don't have to go searching for it. So I'm going to get modified quotas by dividing each population by 9965. So 34,800 divided by 9965, 3.492. 10.52. $6.502. Oops. $14.13. And then 54,800 divided by 9965, and I get 5.499. So if I'm using Webster's method, I just round these standard, right? Below 0.5 down and 0.5 or up or above round up. So this is going to be 3, 11, 7, 14, 5. And does that add up to 40? It does. Is it the same as my apportionment for Huntington Hill? No. So they can sometimes come out differently, but I rigged these numbers to try to make them come out differently. But you can see that the rounding values were always really close to the half, right? They were like 3.49 or 4.486 or something like that. So in general, Huntington Hill and Webster's method are often the exact same apportionment. They often, or usually, not even just often, but usually produce the same answer. Okay, because the cutoff values are always so close to 0.5. They're like 0.48 or 0.49. That they almost always produce the exact same apportionment. So in general, given that, what do you think of Huntington Hill? Yeah. Why though? Way easier, simpler. Mm-hmm. Why do you like Hamilton? Is it as easy as Webster? Really? You think that the rounding rule is easier? I mean, I can just look at a number and know how to round it under Webster's method. Under Huntington Hill, I have to do all these other calculations and decide how to. Simpler, faster, and given that they're almost the same otherwise. Yeah. So why do you think Huntington Hill was recommended then? More accurate how, though? I mean, like, what is it about that rounding rule that would make it more accurate? Yeah, I think that there's something to that. I think that like a couple of things. Like first they asked mathematicians to do this and they were like, we can't just come back with Webster's, you know, like he was just a regular guy. We have to come up with something more complicated than that. Yeah, so they came up with something almost exactly the same, but not quite.
I mean, like, how much time do these people have on their hands? Like,
Well, Congress hired.
And everything else. Just like, how do they take the time to do this all day, every day?
Well, that's their jobs. Their jobs.
I'm all for that.
Okay, so there's a little bit of time left. I think that you should try apportioning with Huntington Hill in your groups.